See if you can guess what these graphs look like as I write them out. We'll start with something simple. F sub 0 of x equals 1. What's your guess? It's just a horizontal line. How about f sub 1 of x equals 1 plus x? That's the y equals x line shifted up by 1. How about f sub 2 of x equals 1 plus x squared? That's a little bit more complicated. That one's kind of like that. You see what we're doing? Every time we add another term, we're increasing its power, the power of x, by 1. And every time we do that, it adds some more details to the graph, some more features. So we'll go up one more graph here, up to x to the 4th. And this one's almost a parabola, but it's got a weird little bump in it. And those are just approximations. But what we're doing is we're adding more details with each term. And the purpose of that is that we're using this polynomial. And polynomials are simpler than other functions. Other functions can be hard to work with and hard to integrate and so on. So we're approximating the features of a more complicated function just by using a polynomial. Now the polynomial that we were writing out here is this one. It just goes up to infinity. Now we can call that s. We'll say that equals s. And then if we multiply s by x, that's going to be x plus x squared plus x cubed. We essentially increase the power by 1. And then if we subtract s minus sx, then we're going to get a whole bunch of cancellation. This will cancel that, and all of them except 1 will be left with 1. And then we can do some algebraic manipulation, factor out the s, 1 minus x equals 1, and then we can just do s equals 1 over 1 minus x. So this complicated, it's not too complicated, but this polynomial, if we continue that up to infinity, that actually equals 1 over 1 minus x. But that's only when the absolute value of x is less than 1. So it's only when x is between -1 and 1. That's called the interval of convergence. Outside of that interval, it diverges. Okay, that's probably a good stopping point. Follow along for more. What even is a Taylor series? Let me try to build some intuition and help you out. Let's say we have this function f of x. We know that if we pick an x coordinate, we'll call that a, then that corresponds to this point here. It'll be a f of a. That's the point. And then we also know that the slope there, the slope m equals f prime of a. Okay, so Taylor series. Let's just look at an example. Let's say we have L of x equals f of a plus f prime of a times x minus a. That's the equation for a tangent line at the point a, f of a. So that'll look like this. Okay, so it doesn't follow the function perfectly. It just shows you a tangent line. But what if we do q of x equals f of a plus f prime of a times x minus a, but then we add another term plus f double prime of a over 2 factorial times x minus a squared. And we'll explain this formula in the next video, like where it comes from. Well, this one might follow the function a bit more closely. It might look like this, for example. So it's getting better. It's not perfect. But what if we do p of x equals all this stuff that we wrote already x minus a plus f double prime of a 2 factorial x minus a squared, and then we do another term, so f triple prime of a over 3 factorial times x minus a cubed. Well, this one might look something like this. You know, it's getting better. So the more terms we add, the closer we get to the function that we're trying to approximate. And sometimes it matches pretty good. Sometimes you can do an infinite Taylor series and it matches the function that you're trying to approximate. You can match it perfectly in some cases. And we'll get into more of that in the following videos. Thanks for watching. What's with the Taylor series formula? Well, let me show you. Suppose you have this function f, and you're looking at a f of a, that point right there. That's the point where x equals a. The purpose of a Taylor series is to build a generic polynomial p of x that matches the behavior of the function f at the point where x equals a. So it goes like this: c sub 0 plus c sub 1 x minus a plus c sub 2 x minus a squared plus c sub 3 x minus a cubed, and so on. So why do we use x minus a? Let me show you. When you take p of a, all those terms drop out except for c sub 0. Now what does this coefficient represent? It's the height of the polynomial that we're building. So we want the height to match the height of f. So we set c sub 0 equal to f of a. Now it has the same height. Okay, let's keep going. Let's take p prime of x. P prime of x. So then c sub 0 drops. We're left with c sub 1 plus 2 c sub 2 x minus a plus 3 c sub 3 x minus a squared, and so on. P prime of a. Again, everything drops except for the first term. Now what does c1 represent? Well, it's the slope. It's the first derivative, so it's the slope here. We want that to match our function. So we set c sub 1 equal to f prime of a. Keep going. Let's take f double prime of x. Okay, c sub 1 drops out. We're left with 2 c sub 2 plus 6 c sub 3 times x minus a, and so on. Okay, how about p double prime of a? Everything drops except for the first term. We're left with 2 c sub 2. So the second derivative represents the curvature of the function. We want that to match f's curvature. So we set c sub 2 equal to f double prime of a. But we have this coefficient of 2 here because we took the derivative. So we have to divide by 2, but not just 2, but 2 factorial. And that's because, look, we have a 6 here. We're going to have to divide by 6 next time. So we're increasing in a way that matches factorials. So, all this to say that is how we get f of x equals the sum from n equals 0 to infinity of f to the nth derivative of a over n factorial times x minus a to the n. We're building a polynomial that matches the behavior of the function f at the point x equals a. We're matching the height, we're matching the slope, we're matching the curvature, and so on. All right, see you in the next video. Thanks for watching. What is a Maclaurin series and why should you care? Before we can answer that, let's review what a Taylor series is. Looks like this. It's the sum from 0 to infinity of the nth derivative of a over n factorial times x minus a to the nth power. So a Maclaurin series looks very similar. So it's f of x equals the sum from 0 to infinity of the nth derivative of 0 over n factorial times x to the n. So we just replaced a with 0. That's it. So the expanded form looks like this. So f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed, and so on. So before we explain why this matters, let's do a quick example. Let's say f of x equals 3x squared minus 5x plus 2. And let's find the derivative. So f prime of x equals 6x minus 5. F double prime of x equals 6. And f triple prime of x equals 0. Let's find the values. So f of 0 equals 2. F prime of 0 equals negative 5. F double prime of 0 equals 6. And f triple prime of 0 equals 0. So now we can use this formula and these values and see what we get. So we get, let's see, f of 0 is 2. And then we'll say plus f prime of 0 times x. That'll be minus 5x. And then f double prime of 0 over 2 factorial. That'll be plus 3x squared. And then this one will just be 0 because we have 0 here, so plus 0. So notice that we just created this exact function. It's just in a different order. You can rearrange it. Same exact function. Okay, so why does this matter? Well, for functions that are more complicated, like e to the x, or sine of x, or cosine of x, or ln of x plus 1, so we can't write these more complicated functions as polynomials directly. But near 0, the Maclaurin series acts just like the function using only powers of x. So that makes approximations, calculations, computer algorithms all possible by working locally around 0. Hope that helps. Thanks for watching. Can you write e to the x as a polynomial? Let's try. We'll use a Maclaurin series. So if f of x equals e to the x, well, that also equals f prime of x, and f double prime of x, and the third derivative of x, and so on. Every derivative is still e to the x. Now what happens when we plug in 0 for x? So f of 0 equals 1, which equals f prime of 0, and f double prime of 0, and so on. Every derivative when x is 0 of e to the x just equals 1. So if we plug this into the Maclaurin series formula, so e to the x equals, this is just the formula for the Maclaurin series. It looks like this: f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus the third derivative of f at 0 over 3 factorial times x cubed, and so on. So that's the Maclaurin series formula. But when f is e to the x, well, that simplifies really nicely. So f of 0 just becomes 1. F prime of 0 times x is just x. F double prime of 0 over 2 factorial times x squared is just x squared over 2 factorial. And this is just x cubed over 3 factorial. And you can see the pattern there. So as these terms continue, they'll eventually start to get smaller and smaller and smaller. And we can use this to approximate e to the x very closely. It's easy to compute, it converges everywhere, it approximates really fast. And what's interesting is that, so most Maclaurin series only work near 0, but e to the x is special in that the polynomial here, it matches the function for all real numbers, and that's why it's really important for calculus. So let's do a quick example. If we take e to the 0.1, we can approximate that with a Maclaurin series, and we'll get 1 plus 0.1 plus 0.1 squared over 2, and that equals 1.105, which is a very close approximation, and we could just do more terms if we wanted to make it even more accurate. Okay, hope that helps. Thanks for watching. Can you approximate sine and cosine using only polynomials? Yes, you can, using the Maclaurin series. Let's do that. So first, let's remember the Maclaurin series formula. It goes like this: f of x equals f of 0 plus f prime of 0 times x, plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed, and that pattern continues forever and ever. So now let's think about the derivative cycle of sine. So if we have sine of 0, the first derivative is cosine of 0. Second derivative is negative sine of 0. Third derivative is negative cosine of 0. And then it just repeats. So we evaluate those. So sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. And negative cosine of 0 is negative 1. So if we plug that stuff back into the formula, we're going to see that sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And it continues like that. So the reason that's happening is that, well, these are canceling out, these are canceling out, and we're only getting the odd terms, the odd derivatives. Cool. So that's the formula for sine of x. And very similarly, cosine of x, pretty much the same thing happens. And we get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus, so we're only getting the even derivatives here, and we're alternating the signs, plus and minus. So quick example using this formula, sine of 0.2. Well, we plug it in here, and if we just use the first two terms, we get 0.2 minus 0.2 cubed over 6, and that is approximately 0.00133, which is just about what you would get by using a calculator using the sine function. All right, hope that helps. Thanks for watching. How in the world can you approximate the cosine function using a polynomial? Well, we're going to use the Taylor series for that. So that's going to be the sum from 0 to infinity of the nth derivative of a over n factorial times x minus a to the nth power. Now, if we were just trying to approximate around the point where x equals 0, we would use a Maclaurin series. But we're going to do it somewhere else, not around 0. So why would we choose a point that's not around 0? We'll take a look at this number line. Say it goes from pi minus 0.1 to pi plus 0.1. So a Taylor series is most accurate near the point that it's built from. So if the function has interesting behavior somewhere near pi, for example, then we should build the polynomial around pi. And then we can get accurate approximations all around here. Okay, so let's expand cosine of x at a equals pi. And let's remember the derivative cycle of cosine. So if we have cosine x, then the first derivative is negative sine x, second derivative is negative cosine x, third derivative is sine x. Now if we evaluate each of these at x equals pi, then we get, well, cosine of pi is negative 1, this will be 0, this will be 1, and this will be 0. Now if we plug those into the Taylor series structure, we get cosine x is approximately negative 1 plus 0 plus 1 over 2 factorial times x minus pi squared plus 0, and so on. The zeros are, oh, I didn't put 0 here. Yeah, so the 0 terms are dropping out. Okay, and we went over that in the last video, how that works. So the approximation using the first couple of terms, cosine of x is approximately -1 plus x minus pi squared over 2. Let's give it a shot. Let's pick a nearby point. Let's say x equals pi plus 0.1. So we plug that in. Cosine of pi plus 0.1 is approximately -1 plus 0.1 squared over 2. We're just plugging in there. And that is approximately -0.995. If you plug that into the calculator, you'll get a very close answer. All right, hope that helps. Thanks for watching. What if you need to create a new Maclaurin series? What should you do? Well, let's take e to the x, and recall that that is 1 plus x squared over 2 factorial, and so on. If you need to find e to the 3x, well, then you just replace x with 3x everywhere. So 3x squared over 2 factorial, and so on. You can do that with other functions too, like sine of x. Okay, another example. Let's say you need to find e to the x plus x squared. Let's just write that out. X squared over 2 factorial, and so on, plus x squared. So you just combine like terms. So that will equal 1 plus x plus 3 over 2 x squared. And then you continue with the rest of the series. So we only need to worry about the x squared term. Okay? How about multiplication? So what if we want to find 2e to the x? Well, we just multiply every term by 2. So that'll be 2 plus 2x plus x squared, because the 2's cancel out, and so on. Okay, more complicated example here. What if we want to find e to the x times e to the x? Well, we can just write out a piece of each of the series. And you could do this if you had different series as well. So 1 plus x plus, and so on. Okay. So we can think of each term as combining with every term from the other series whose powers add to the same degree. So we do it like this. So the constant term would be 1 times 1, which equals 1. And then the linear term would be 1 times x plus x times 1, which equals 2x. And then the quadratic term is 1 times x squared over 2 plus x times x plus x squared over 2 times 1, and that equals 2x squared. And you would do that for every term, for as many terms that you want to see, and we would get e to the x times e to the x equals, well, we have 1 plus 2x plus 2x squared, and so on. Okay, hope that helps. Thanks for watching. How good is a Taylor series approximation? Well, we can use the error to find out. Let's write down the error. So f of x, here's the Taylor series formula, f of 0 plus f prime of 0 times x, all the way up to the nth derivative of f at 0 over n factorial times x to the n, plus, here's the error, r sub n of x. So this is the approximation, and that's the leftover piece, that's the error. Okay, so what makes the error small? So near the center, which here is 0, the polynomial and the function line up well, but further away they drift apart, and that drifting is the remainder. So here's the formula, r sub n of x, the remainder, is less than or equal to big M over n plus 1 factorial, absolute value of x to the n plus 1 power. So m is any number bigger than the n plus 1 derivative on the interval between 0, because that's what we're centered around, and x. So the formula gives a safe upper limit for the error. Here's an example. If we say e to the x is approximately 1 plus x squared over 2. Well then, so derivatives of e to the x are all e to the x. And near 0, e to the x is less than or equal to e. So let m equal e. Okay, so this works for small x, like absolute value of x is less than or equal to 1. So plugging that into the formula, r sub 2, because we're using the second derivative right here, we're just using this formula, plugging everything in, less than or equal to e over 3 factorial absolute value of x cubed, which equals e over 6 absolute value of x cubed. So the difference between the true value and the polynomial is at most this right here, e over 6 times absolute value of x cubed. Smaller x means smaller error, and more terms means more accuracy. So we can use the remainder as a bound to see how good the approximation really is. Okay, hope that helps. Thanks for watching. Why should we care about Taylor and Maclaurin series? Well, they help us estimate, predict, and compute in ways that are often easier than working with the original function. So for example, here's how we can approximate small values. So sine of 0.2 is approximately 0.2 minus 0.2 cubed over 6, which equals, it's approximately 0.1987. So without a calculator, we can approximate sine of 0.2 by just a few terms, and the remainder tells us how far off we might be. Next thing, so for physics, so many physics problems involve functions like sine and cosine near equilibrium points. So we can linearize the system, just the first term or two, to simplify analysis. We can say sine of x is approximately x for small x. Okay, so another thing is differential equations. So Taylor expansions can help solve differential equations where exact solutions are hard. Instead of using an exact function, we generate a polynomial solution term by term. So if we have y prime equals y, then we can say y equals 1 plus x squared over 2, and so on. Next thing we can do is we can approximate integrals. So sometimes integrals are tricky or impossible to do exactly, so we can replace the function with its Taylor series and integrate term by term. For example, if we have an integral from 0 to 0.1 of e to the negative x squared dx, we can approximate that by using the Taylor series, 1 minus x squared plus x to the fourth over 2 minus etc. Much easier to integrate that. Computer algorithms, so computers, calculators, simulations, they use expansions to approximate functions efficiently and accurately. So through this series, we saw functions as infinite sums, how to build Taylor polynomials, how to estimate error, practical ways to use these approximations. I hope this series was helpful for you, and as always, thank you so much for watching.